Thank you very much, Stephen, for that excellent paper. He has certainly given us a lot of food for thought. It's a pity you were not here yesterday. We did have two excellent presentations dealing with utilities, both TSTT and TNTech. And the committees established by these bodies should get involved in what Stephen has been proposing. Okay, and I'm sure APET will also become involved in some of the committees being proposed by Stephen under the aegis of ODPM. I'm very glad to see that our speaker has arrived so that we don't have to amend the program.
Yeah, let's go with Chris.
Eh?
Let's go with Chris.
Oh, you want? Okay, I've been advised that a slight change in the program. We will take Chris Braden, Billy Aluwaya, and Chris Ray's paper entitled Seismic Modeling of a Multi-Span Semi-Integral Bridge first before Ms. Engineer Albada's paper. We'll give him some time to settle down. Right? So let me introduce, the paper will be presented by Engineer Chris Ray. And for those of you who have the booklet, on the abstract booklet, Chris has 19 years experience in the transportation engineering industry, working on various highway structural design projects throughout the world. He earned both the bachelor's and master's degree from the University of Florida in Gainesville. For those of you who are familiar, I understand there's a very good agricultural faculty. And in fact, my brother-in-law's son went to the University of Florida to do a degree in agriculture, and he's now assisting his dad in, some of you would know, La Vega Estate, right? Anyway, that's a plug for him. Chris is a registered professional engineer in the state of Florida and the author of a large wind missile impact performance of public and commercial building assemblies. Chris has worked on segmental and post-tensioning projects in the United States, Israel, and currently here in Trinidad and Tobago. His experience also includes the design and detailing activities relating to pre-stressed concrete, steel box girder and plate girders, and temporary works such as sheet piling, strongbacks, incremental launching, and false work systems. He has worked on more than a dozen segmental projects, including the Frederick Douglass Bridge, Bonner Bridge, and Kanawha River Bridge, the longest span concrete box girder bridge in the United States. So Chris brings to us a wealth of experience in the field of bridge engineering, and he will now present to you his paper, Seismic Modeling of Multi-Span Semi-Integral Bridge. I invite Chris to the podium. Thank you.
I'd like to start by thanking APET for inviting me. It's been very interesting and beneficial to be able to come down here and see some of the perspectives of other disciplines and the Caribbean in general, as you know, things are slightly different as they are in the U.S. But more importantly, it's been a really long time since I've had doubles, and so I've had the opportunity to get some of those on this trip. So hopefully my presentation will extend Dr. Ramroot's presentation about structural integrity and earthquakes, although I do take exception with the statement that we know what we're doing half the time. I like to think that's more like 60% of the time. So today I'd like to do an introduction on why we need to consider seismic action and what it can do to structures, and also go over some analysis methods, structural systems, and focus in on semi-integral systems and what their advantages are. And I'd like to finish up with some of the structural modeling to determine the seismic loads on a bridge. So structural design in an active seismic zone can require careful consideration of a lot of parameters. A design engineer needs to consider a lot of parameters like seismic return period, which is a measure of a earthquake's severity. Longer return periods equate to larger earthquakes. What the accelerations on the structure will be, how these structural materials respond. Concrete obviously works a little bit different than steel. How the different structural members behave. A I section will behave differently than a 1.2 meter drilled shaft concrete section, and how the structure interacts with the soil surrounding it. Failure to properly consider these effects can be disastrous. They can cut off links between rural communities, also large interstates in the United States. There could be significant loss of life in a structural failure. This was some of the earthquakes a few years ago in Northridge and the Loma Prieta earthquake. Trinidad and Tobago is located in a seismically active region, as Mr. Gill pointed out yesterday. This is a map from the University of West Indies Seismic Research Center showing a grouping of all the seismic events in the region, and their circles represent relative magnitudes. Trinidad is located in a boundary zone between the Caribbean and North American plates. They move by approximately 2 centimeters a year relative to one another, and for us Americans in the room, that's about 3/4 of an inch. And rather than moving continuously as a smooth surface against smooth surface, they tend to lock, and then the restraint force is erupted all at once, causing an earthquake. Here you can see, this is a soils map of Trinidad, and down here in the south of the island, there's a very clear delineation here along one of the fault lines, where you can see that the soils to the west of the fault line match up very nicely with the soils to the east, and you can see some of the relative movement between the two plates. For reference, this is the Sir Solomon Highway extension project that's currently under construction. Some of you may remember last year there was an earthquake to the north of Venezuela that was reportedly felt on the island. That's not too far away from Trinidad. Had it been closer, you may have suffered some more damage than was actually experienced. So now I'd like to talk about some analysis methods. The American Association of State Highway Transportation Officials has the design specifications that's used in the United States. They have a various number of analysis methods that can be used, and they prescribe which can be used when. Based on the importance of a bridge, which is a parameter that is defined by the owner, the regularity of the bridge, which is a measure of the relative span lengths and skew, curvature, that sort of thing, and the seismic zone. The seismic zone is a measure of the risk of a seismic event for a particular structure. Generally down in Trinidad, we're in seismic zones 3 and 4, and these are the various analysis parameters that you're allowed to use. So for a relatively simple bridge in a seismic zone 2, you can use a single mode or uniform load method. As you get into critical bridges in higher seismic zones, it requires a more thorough time history analysis. There are simplified methods for a single span bridge. All you need to design is the connection force between the superstructure and the substructure. This can be essentially a force equals mass times acceleration calculation. For semi-integral bridges, which is what I'll be talking about today, this can be used to size the back wall, which is what will actually be taking the seismic force. Another method that is related is the Mononobe-Okabe method. This is a a seismically altered coefficient of active earth pressure that's generally used for retaining structures, but it is a static analysis to approximate a dynamic effect. And there's no special software needed for these analyses. The most onerous is the time history analysis. It's required for the most complex, largest, most expensive bridges. It uses seismic acceleration data from actual earthquake events in the United States. That's generally the Loma Prieta earthquake or the Northridge earthquake in California. These are computationally very expensive. Even the most state-of-the-art, high-powered machines can take hours or days to run through an analysis, depending on the bridge complexity. In general, a response spectrum analysis is used. This is a plot of peak performance versus frequency or period, and it allows a design engineer to consider multiple events and frequencies within a single analysis. It can either be used for a single mode or multi-mode response, and for structures requiring a multimodal analysis, AASHTO requires that a three-dimensional model be constructed, and the number of modes that you must consider must be at least 3 times the number of spans. So for the 3-span bridge that I will go through in a bit, that's 9 modes of behavior. I've mentioned structural modes a few times. That relates to the structural behavior at various natural frequencies. So in this animation, sorry. For the first mode, in the natural frequency of about 1.7 hertz, it moves in one way. For mode 2, it is a completely different motion. And for modes 3 and 4, they are again different motions. So the same structure based on different vibration frequencies can behave differently. The response spectrum is constructed using 3 seismic parameters. The profile ground acceleration and the 0.2 and 1 second spectral accelerations. This is the curve that is used to relate the acceleration with the period. There are a couple of different structural systems that can be used in a seismic zone for a short to medium span bridge. The first one being an integral structure, and the second being semi-integral. An integral superstructure is connected to the substructure. Here we have a diaphragm at the end of the beams, and this is tied in to the abutment cap with reinforcing, and this creates a rigid connection between the girders and the abutment wall. Because all of the load is transferred into the substructure, it is the components are generally larger and therefore more expensive than the semi-integral counterpart. For the semi-integral, the superstructure sits on bearing pads and is partially isolated from the substructure system. This allows the superstructure to move freely or restrained only in the ways that we want, and prevents a lot of the seismic and thermal loads from being introduced into the substructure. This, of course, less load equates to smaller components, which relates to cost savings. So where does the load go if we are not connected to the substructure? The semi-integral system is generally restrained by the passive resistance of the soil. So as the longitudinal motion of the superstructure gets pushed into the soil, you gain a resistance from that soil. Likewise, as the bridge moves to the side, you gain a resistance on the fin walls that are that are hanging from the diaphragm. In general, bridges have retaining walls or slopes on either side for grade separations, so in general, the leading edge is not considered, as the soil cannot often be considered as fully active. You can use several fin walls, but the danger in using that is you need to make sure that the failure plane of the soil does not intersect with the adjacent walls. This can cause a reduction in the capacity of the soil, and therefore you're not going to get the resistance that you're expecting. If we want to, we can use other components to help carry the seismic motion. At the piers on this multi-span bridge, we have shear keys with bearing pads interlocking with the superstructure diaphragm. This helps engage the pile and produce an additional resistance beyond what is available from the passive resistance at the ends. And here I'd like to walk through a animation of how all these pieces fit together. So here we have a 3-span. This remote doesn't like playing videos. We have a 3-span pre-stressed girder bridge over a river. As we dial in, it's sitting on board cast-in-place piles at both the abutment and at the piers. Here is the semi-integral system I just went through. We have the diaphragm in between the girders. The girders are cast in, and there is reinforcing running through the girders. We have a shear key to interlock with the diaphragm, a wing wall and fin wall to, again, take the lateral motion of the bridge. And here's how that fits in with a suspended back wall and diaphragm, and this whole system takes the passive resistance of the soil. As we move into the pier, we have the vertical shear keys with vertical elastomeric bearings to tie in with the diaphragm. Each girder from the adjacent spans is tied together in one heavy diaphragm, and here you can see the keying in. So as this moves, it'll engage that spring in the bearing and engage the piles. So all of this needs to be modeled somehow. Again, AASHTO requires a 3-dimensional analysis. This is utilizing a finite element software called MIDAS. And it's very important to model the actual geometric and material properties of the structure. Seismic analysis is very dependent on relative stiffnesses and performance of the materials. So it's critical so that the stiffness of the bridge and the motion of the bridge is captured, but it's also important so that the mass is correctly distributed throughout the structure. The soil structure interaction is very important, as we're relying on that to carry the load. Soil behaves non-linearly, and therefore either nonlinear springs need to be defined or an iterative solution needs to be used. In reality, soil is not very good at taking tensile load. So in your actual structure, this is a idealization of what's happening. For modeling efficiency, you can also use a tension spring to model the opposing compressive spring. Where soils may be subject to liquefaction, it's important to examine both the static and the liquefied states of the soil. Seismic can be counterintuitive in the sense that the liquefied soil will produce a taller column, but in seismic design, stiffness is the enemy. It's going to draw more load, so as the pile gets longer, it becomes more flexible and allows a freer movement of the structure. So both conditions need to be made because one condition may control for one component, another condition may control for another component. The bearings that we looked at before can be modeled as springs. Finite element software likes to put a single member with the section properties of the component you're looking at. It's important to provide rigid offsets so that the actual depth can be modeled. A horizontal motion of this at a distance is going to cause an additional torsional moment in the cap, and so it's important to model that with rigid offsets so the geometry actually fits together the way it's supposed to. Here is a definition of the response spectrum. It's important to make sure that dead loads are modeled as masses. In this particular software, just because I add a dead load of a barrier in doesn't necessarily mean that that's going to be included as a mass in the structural analysis. So once those are defined and the response spectrum is defined, you run the analysis. Now, AASHTO requires that you look at both the longitudinal and the transverse motion of the bridge, and that those be combined using 100% of the longitudinal response with 30% of the lateral, and vice versa. So you have a resultant effect in a diagonal direction. So in the end, design of a multi-span bridge in a seismically active region, such as Trinidad and Tobago, requires a refined analysis. And use of a semi-integral structure greatly reduces component sizes and therefore the cost, which generally makes the owner happy. It lends itself to more flexible elements, and the seismic loading is primarily resisted by the passive resistance of the soil at either end of the bridge. Use of a 3D model to determine the structure's seismic response is required by AASHTO, and a response spectrum analysis is the most common way to perform that analysis. It's important to model the soil structure interaction accurately, otherwise the structure will behave differently than you're intending, and accurate modeling of the bearing springs is also required.